For translational motion, we have linear momentum equals to mv. And here we have angular momentum, that is I omega. By the way, if we say momentum or velocity, we mean the translational kind. For the rotational kind, we would say angular momentum and angular velocity. And for point mass, the angular momentum can be found as I omega. We can also use perpendicular r times mv, which is also perpendicular r times the linear momentum. Linear momentum is conserved if the net force on the system is zero, or the linear momentum of an object is conserved if the net force on that object is zero. The angular momentum is conserved if the net torque is zero. And we have linear impulse. We also have angular impulse. Angular impulse is the average torque times time. And if this is the net torque, then the angular impulse by the net torque equals to the change in angular momentum. Angular momentum, which is I omega, is conserved if the net torque is zero. For example, we can have a spinning ice skater pulling the arms and legs in. When the person pulls the legs and arms in, the mass distribution is closer to the axis, so the rotational inertia decreases. Since L has to be a constant, that means the omega would increase. Or we can have a rotating merry-go-round, and this person standing on the merry-go-round walks towards the rim. When the person walks towards the rim, the mass distribution gets farther away from the axis, so the rotational inertia increases, which means the omega would decrease. Or we can have collision problems like these. These are both top views. A person is running towards a merry-go-round that is at rest, and then the person jumps onto the merry-go-round. So they collide and then they stick together. In this process, the angular momentum is also conserved. The person coming in is a point mass. So the person's initial angular momentum would be the perpendicular r times m times v. The perpendicular r would be the distance between the line of motion and the axis. So this is the perpendicular r. When this person lands on the merry-go-round, they'll rotate together. In this collision, the net torque on the system is zero, so the angular momentum is conserved. So this initial angular momentum is going to turn into the angular momentum of the person and merry-go-round combination. But if the person runs like this towards the center of the merry-go-round, then the person would have no perpendicular r. That means this person, when he jumps onto the merry-go-round will stay at rest because the initial and final angular momentum should be equal to zero. Same thing here. If you shoot a dart into a wet bar of soap, the soap-dart combination will start rotating. There is an important difference between these two. That is, for this merry-go-round, there is a fixed axis. That means the net force on the system is not zero when the person jumps onto the merry-go-round, because when the person lands on the merry-go-round, the force on the axle would change. So the net force on the system is not zero. However, whatever extra force that's at the axle when the person lands, the force through the axle will give no torque. Therefore, we can have net torque being zero, while the net force on the system is not zero. But in this case, there is no fixed axle. So when the dart hits the bar of soap, we would have both the net torque being zero and net force being zero, which means in this case we would have both the angular momentum conservation and the linear momentum conservation.